So we've spent all this time figuring out blood pressure, mechanisms that really can change blood pressure. If you increase your heart rate, you can increase stroke volume and blood pressure. If you decrease heart rate, you can decrease your blood pressure. If you increase stroke volume, you can increase blood pressure. And all of this stuff, I mean, let's just draw it out. We have I can do this. We have little sensory receptors called baroreceptors. Baroreceptors. They're sensory stretch receptors found in your big blood vessels. And the baroreceptors receive information about stretch or pressure, and they send a message to the medulla. Who's this going to be? The medulla oblongata. The medulla oblongata is in your brain stem and is going to receive the message and go, oh, baroreceptors are stretching too much. Blood pressure must be too high. Send the message to, oh, where? What could we possibly do if blood pressure is too high? Let's go. We could change heart rate. Heart rate. If you change heart rate, that substances that change heart rate are called chronotropic. Chronotropic. Where did that come from? What is that thing? Look, I can get rid of it. Chrono, except now I say chronotropic. How's that? Chronotropic substances change the heart rate, as opposed to what's something else we could change. We could be an inotropic substance and change contractility or force of contraction. I like force better. So we can change the contraction force. Inotropic substances will do that. Or we can change the heart rate. Chronotropic substances will do that. Those are two options that we're like, we got this. We've got all the pieces that will let us do that. Well, there's something else that we can do that doesn't have to do with the heart. And it has to do instead with the peripheral vasculature. We can change vessel diameter. And I want you to think about this for a second. If we're changing vessel diameter, the other words that we can use for this are vasoconstriction or vasodilation. And think it through. If we vasodilate, what's going to happen to blood pressure? If nothing else changes except we have vasodilation, do you agree that vasodilation is going to create a bigger lumen, and that's going to decrease resistance, which is going to decrease blood pressure? If we vasoconstrict, nothing else changes, then we're going to increase resistance, which will increase blood pressure. By adjusting the diameter of blood vessels, we can also modify blood pressure and adjust as necessary. Now, oh gosh, what was I going to say? There was something awesome that I was going to tell you. Oh, what vessels can this happen in? You tell me what vessels can change diameter. Well, let's go back and look at our vessel chart again. And then, whoa, you tell me who could possibly change diameter. Well, we only have 3 people who can change diameter, who could possibly change diameter. The arteries could change diameter, the arterioles could change diameter, and the veins could change diameter. Only people who have smooth muscle can change their diameter, because the smooth muscle, just like in digestive histology, we've got those rings of smooth muscle surrounding our digestive gut tube. It's the same thing with our blood vessels. We've got rings of smooth muscles. Do you think arteries are going to be the primary place where vasoconstriction is going to have, or vasodilation is going to have an effect on blood pressure? No, it's actually the arterioles. This is where the majority of adjustment can take place. Arteries and veins are too big. I mean, awesome, you can totally vasoconstrict and vasodilate your arteries and your veins, but you're not, they're huge, and where are you going to push the blood if you vasoconstrict and vasodilate those guys? You're going to push it back into the arterioles. If you vasoconstrict and vasodilate your arterioles, you really can generate a great deal of difference or change in where your blood is distributed, which will ultimately affect blood pressure, which is kind of interesting. Okay, changing the diameter of your arteriole, there's a couple of things, couple of ways that this happens. There is a whole mechanism by which your arterioles, the smooth muscle, stretches, and stretch receptors in the smooth muscle itself automatically respond in a reflexive vasoconstriction. So when pressure gets really high and does a big stretch, they vasoconstrict, and they're going to like shut down almost, like no blood can come through now in this area. It's kind of an automatic self-regulation. They also will respond to different chemicals. So paracrine chemicals from neighboring cells that are doing various jobs. If they're producing a great deal of carbon dioxide, indicating a lot of metabolism, a lot of activity happening, then those arterioles may vasodilate to allow more blood in to get rid of the carbon dioxide and bring in more oxygen. Increased metabolism can be represented by or can be indicated by the amount of carbon dioxide in the blood. So you have all of these. I'm pretty much going to stop here because the complexity of response possibilities with blood pressure, like how your body responds to changes in blood pressure outside of that homeostatic range, is vast. And we're coming back to blood pressure because the kidneys play a huge role in blood pressure homeostasis, and we're not doing those guys until like way down the line. We're going to be peeing in cups, and it'll be super fun. I mean, super fun. All right, the last thing I want to do is walk you through, I think I'm just going to use an old video for this piece. I'm going to walk you through how to take blood pressure clinically, and then we're calling it a day. That's all. Okay, bye.